blood is. And that's a good deal. Now, if we were a little desert rat, okay, and we only got to drink water about 3 times a year when it rained, we would really make concentrated urine. And they might make urine up to 6,000 milliosmoles per liter. That's pretty damn strong stuff. But they don't have any water, because they're not drinking all the time, to pass all that stuff out. So they need to be able to concentrate their urine more. Okay, this is a slide that appears at this point in the lecture. It may seem a little bit out, but I'm going to tell you 6 numbers that you just got to know. And we're going to be talking about them for the next few weeks as we talk about fluids and electrolytes, not next few weeks, next few days. There's a thing that we used to order every morning on every patient that was in the hospital, especially if they had an NG tube or if they had an IV, and it was called an SMA-6. SMA was just the name of the company that made this analyzer machine that sat in the lab, and they'd get a tube of blood, spin it down, take the plasma off the top, run it through the test. And these are the 6 numbers that we would get every day. And as we go through the study of these fluids and electrolytes, you just kind of got to know what normal is, okay? And those normals are sodium is about 140. I'm giving you nice round numbers to learn, okay? Potassium is about 4. Chloride is about 100. Bicarb is about 24. Glucose, about 100. If you're diabetic, you can go up to 1,600. But if you're pretty normal, it's going to bounce around 100, depending on whether you're eating or not. Yeah.
What's the unit of measurement for this?
These are all milliequivalents per liter. Very good question. Milliequivalents per liter. And remember, an equivalent is depends on the molecular weight of these different things in terms of. But we're just going to kind of talk in terms of when you simplify it to milliequivalents per liter, then you're comparing apples to apples, sort of. Glucose is about 100. BUN is about 10. What? Bilirubin is blood, urea, nitrogen. In other words, it's basically how much urea do you have in your body. Okay? Now, you see there's all these other things over here, and I'm just going to tell you a couple of quick points about them. We normally should not have any glucose going out in our urine. Diabetics will. If their blood sugar is really high, they can't reabsorb it all back in. But in our plasma, it should be about 100. We should not hardly have any fat, any lipids in our urine. It's normal to have some fats in our blood. Remember that HDL, low LDL, and all that stuff, as well as chylomicrons. Amino acids. It's not unusual that we spill amino acids. Now remember, it's not usual for us to spill proteins, but it's not terribly unusual for us to spill amino acids, especially after a high protein meal. So amino acids can get into our urine. Proteins should not hardly ever, but they do a little bit. And so forth. Here's the others. Here's the urea. Creatinine, remember, is that muscle breakdown product. The nice thing about creatinine is that we're all breaking down muscle at about the same rate every day, depending on our size. That's why creatinine is kind of a helpful number. We should not have any ammonia in our bloodstream. Remember, we said it's very toxic, and so it should be less than 0.1. It's not unusual for us to pee out some ammonia, but we pee it out right away before it builds up and gets toxic in us. And then uric acid, the same deal. We should be passing most of it out in our urine, plasma. Do not know any of these. You don't have to know any of those numbers. Just know in general that I said you shouldn't really have much protein. You shouldn't have any glucose going out in your urine on a normal level. But these things here, we're going to be talking about a fair amount over the next couple of days. Now, what do we mean when we say pumps? We're talking about things going in and out, right? How does this work? Well, you remember the simplest form of fluids coming in and out through a membrane was simply osmosis. water went through the membrane in order to try to make everything the same concentration. But we have these others, and I'm not going to ask you to memorize these exactly either, but just know there's a little bit you need to know through your PhysioX. How many have done the PhysioX so far? You remember reading about these? Yeah, see? Pretty cool, right? Facilitated diffusion, active transport. Active transport requires ATP, it requires energy. Facilitated diffusion doesn't. It's a passive thing, but it needs some little things to help it facilitate that diffusion. Co-transport is usually when we're transferring things, one in and out and one out, sort of the same as counter-transport. Just know that those are all specific mechanisms that our cell membranes have to move things back and forth. As far as how do those things work and how does our body really do that, just a couple of generalized points about these different forms of carrier-mediated transport. If you want to get a specific substance into a cell, you need the specific carrier protein. Okay? In other words, glucose has specific carrier proteins that are going to move glucose in. There's going to be others for these different electrolytes and so forth. Usually a given carrier protein will only work in one direction. It'll either bring the glucose in, and it might take another carrier protein to pump the glucose out, for example. They may not be equally scattered throughout the whole cell membrane, and just remember that the membrane of a single tubular cell, remember those cells that are in the thick parts of the tubules, what we're talking about here, they may have many different carriers embedded in their membrane. Okay? Carrier proteins like enzymes can be saturated. Let's just say we have 100 pumps of little carrier proteins to pull sugar in. But instead of having a normal sugar level of 100, we've got 1,000 of it. See, we don't have enough carriers to pull that sugar in. So that's what this is talking about down here. And that becomes clear to you from your PhysioX. Quick comments on this. The transport mechanism, transport maximum. How much sugar can we pump out of our urine, for example? In other words, we'd like to pump it all back in. We don't really want to pass sugar out in our pee. We'd like to save it all. But we have a certain amount is all we can pump back in. And if the concentration gets higher than that, what happens? We can't pump it all back in, and it just goes on and passes out in your urine. Okay? So each thing in the urine has a level at which it can't exceed. And we call that the renal threshold. Now there's only 2 thresholds I'm going to ask you to know. And I wrote you a little note down here. Don't miss your PhysioX. So if the renal threshold is basically the plasma concentration at which a specific compound or ion starts to be passed on out in the urine. We want to suck it all back in, all right? We want to pick it up with carriers and bring it back into our body, keep it in the cells of the tubule, not lose it. But there's a certain point where we can't. One that you need to know here is glucose. The renal threshold for glucose is about 180 milligrams per deciliter. Now, what did I tell you normal blood sugar was? 100. So if your blood sugar is almost double what it ought to be, 180, that's the point at which you're going to start spilling sugar in your urine. And if you're doing dip tests for sugar, you're going to have sugar in your urine. And that used to be the only way my grandfather could figure out whether his diabetes was under control. They didn't have those little fancy things where you drop of blood. You know, they didn't have any way to figure out blood sugars back in the 50s, 60s, 70s, and 80s. All they could do, every morning he would get up, he would pee in a jar, he would dip a dipstick in there, and it said 1 plus, 2 plus, 3 plus, or 4 plus sugar. And he almost was spilling almost every day because he was a pretty severe diabetic. And he would look at that, and then the doctor said, well, if you're 3 plus, give yourself 18 units of insulin. If you're 4 plus, give yourself 24 units of insulin, and he would draw it up out of a little bottle and shoot it in his leg. And that was the only thing they could do. Now, today, you can take a little finger pricker thing and put a little hole there and get a drop of blood, touch it to a piece of paper, and within 5 seconds, it will tell you exactly what your blood sugar is. 108, 210, whatever. That's much more valuable than measuring just the urine, right? So then you can base your insulin dosage on that for diabetics. Now, probably more important than any of these things we've talked about here is that today you can even get a little thing, it's a little pump that fits on you here, and it scans your blood sugar right through your skin all the time, and it says, okay, your blood sugar is 120, and the pump will automatically pump in 2 units of insulin. The next hour it'll read your urine again, it'll read your blood glucose again, and decide what dose of sugar you need, what dose of insulin you need. When urine appears in your...
So it's measured in your urine though? How?
I'm sorry?
It's measured in your urine with that pump?
No.
No, it's measuring it in your blood.
Okay.
You're wearing it around your belt right here, and it's got a little needle, and the needle goes under the skin to inject the insulin into you. The
Gotcha.
insulin is carried in the little pump thing there. So when you get glucose spilling out in your urine, in other words, you've gone above this renal threshold of 180, you're spilling sugar, and we call that glycosuria. Not glucoseuria. That makes you sound like a redneck from eastern Tennessee or something. It's glycosuria.
You making fun of him?
You mean brush.
I'm not going to go any further. The other one I wanted you to know about was amino acids, because we have a renal threshold for amino acids. I told you it wasn't terribly unusual for you to spill some amino acids once in a while. We can only suck back in about up to 65 milligrams per deciliter of amino acids. So if you eat a really hot protein-rich meal, you're probably going to spill some amino acids. It's not really abnormal. It's called amino aciduria. Get it? Amino acids in your urine. I'm going to show you a little video over in lab about countercurrent multiplication, so I'm not going to do it here. I think you all should understand, you should have understood this back in 112, the concept of osmolarity. You remember that? Like when you drop a molecule of NaCl, it splits into A and it splits into Na and into Cl, and that's 2 things that are now in solution. And osmolarity is just a measure of how many things are in solution with you. Spread to milliosmolar. Our blood is about 300. We said earlier that we can concentrate our urine up to about 12 or 1400. But all of our body fluids are always the same. Our osmolarity is kept very, very constant. Now, why do you think it's the same in all the cells in your body? Well, homeostasis, yeah, but why? Why does it stay so?
Because all the cells have the same.
No, not pH either.
All the cells have the same basic.
All the cells are surrounded by a semi-permeable membrane.
It's the same membrane, so it's going to be the same.
And so the water, and there's water in every cell and water around every cell, the water can either go into the cells or out of the cells, and it does. That's called your basic osmosis, and that happens so every cell in our body pretty much stays at the same osmotic concentration. You kind of got to understand, you asked me about the units earlier, that was really a good question. Our ions, the sodium, potassium, bicarb, all that stuff, it's measured in milliequivalents per liter. The large organic molecules are in grams or milligrams per liter. That would be like sugar or proteins. I think I've talked about all of these things here. I'm not going to talk about the countercurrent multiplication because I have a little video. And I would also tell all of you who have a chance to go to an open lab, ask Melissa. She gives a really nice little on the whiteboard presentation of countercurrent multiplication that will help you. But basically, just so you understand, countercurrent means that the blood, the filtrate is going one way, and right next to it there's fluid going the other way. And as you suck things out of this one and put it in that one, it gets more concentrated, and then as you go up the stream, it gets more and more and more concentrated. That's the idea of countercurrent exchange. I'm going to I don't want to slip through this. And this is the way I explain it. Let's go over to the lab and we're going to finish up a little bit more about this.